Example 4. Analyze the graph of q of x equals x squared plus x minus 6 over x plus 1. So we're looking at the domain first of this rational function, so we know that any zeros of the denominator we will have to exclude from the domain. So we can see the 0 of our denominator. If we set x plus 1 to 0, we get an x value of negative 1. So our domain will be all the x's such that x is not equal to negative 1. Now we want to look for any holes in the graph of this function. So we'll have to factor our numerator. So we can see this will factor into x plus 3 times x minus 2. So we see there are no factors common to the numerator and denominator, so there are no holes. So there are none, and this is because no factors common to numerator and denominator. Okay, now we want intercepts. So for our x-intercepts, we know any zeros of our numerator will cause the whole function to equal 0. So we're just looking at our numerator, and we can see the zeros of our numerator are negative 3 and 2. So we'll have our x-intercepts, negative 3 and 2. So if we want to write our ordered pairs, and then our y-intercept, we want to evaluate our function when our x is 0. So we want to find q of 0. So we want, and you can put it into the factored form or the original. So if I put it into the original, 0 squared plus 0 minus 6 over 0 plus 1 gives us negative 6. So we have a y-intercept at negative 6. So we have the point 0, negative 6. Now our function's already in lowest terms. There were no factors that were common that we needed to reduce. So now any zeros of our denominator will cause vertical asymptotes. So we will have a vertical asymptote at x equals negative 1. Now we want to determine if we have horizontal or oblique or neither. So we'll compare the degree of our numerator and denominator. So we can see the degree of the numerator is 2, the degree of the denominator is 1. So remember, when the numerator is exactly 1 degree higher than the degree of the denominator, we're going to have an oblique asymptote. So we'll have an oblique asymptote. And if you want to make a note here, that's because degree of denominator is exactly 1 less than the degree of the numerator. So to find our oblique asymptote, we're going to do long division. So we're going to divide our denominator, our x plus 1, into our numerator, x squared plus x minus 6. So we'll do our long division. So x squared divided by x is x. Multiply down, x times x plus 1 will give us x squared plus x. We'll subtract, and we'll be left with nothing. And then if we could bring down the negative 6, but we're done here because x1 will not divide into negative 6, and we don't care about any remainder of the division. We only care about the quotient. So up here, y equals x. That's the equation of our oblique asymptote. So we'll have an oblique asymptote at the line y equals x. Okay, now we want to check if our function will intersect that oblique asymptote. So I'm going to set my function equal to x. So I'll say x equals, and I'll use the factored form, x plus 3 times x minus 2 over x plus 1. Because if this graph crosses this line, y equals x, that means that its y value will equal x at some point. This function will equal x. So we could multiply by the least common denominator or cross-multiply. Either way, we'll get to the same place. So we'll have x times x plus 1, so x squared plus x equals x plus 3 times x minus 2. If we multiply out on the right side, we'll get x squared plus x minus 6. If we collect our like terms, we're going to get, if we subtract x squared from both sides, they're eliminated. If we subtract x from both sides, those are eliminated, so we're left with 0 over here. So we're left with 0 equals negative 6, and that's obviously false, and there's no solution to that. So that means that our graph does not intersect the oblique asymptote, so no intersection. So now let's graph this on our calculator here. So we want to graph our numerator, enclose the entire numerator in parentheses, x squared plus x minus 6 divided by x plus 1, and close those parentheses. Now I'm also going to have us graph on the same axes that oblique asymptote, the y equals x. I'll show you so we can compare those two. So I'll graph on a standard viewing window, zoom 6. There's our graph of our function, and then there's the graph of the line y equals x. So I want to show you that this is when we're in the standard viewing window. If we zoom out, so option 3, and then hit enter, if I zoom out, there's my function, and there's the graph of my line, y equals x. So you can see that in the middle, they look different, but on the ends here, it just approaches, it looks like the line y equals x. That's the definition of the oblique asymptote. As the x gets large, our function approaches that imaginary line. So we can make our graph now. So we have a y-intercept of negative 6, so we need to go down to negative 6, at least. Okay, so let's sketch the asymptotes first. So we have a vertical asymptote at x equals negative 1. And then we've got that oblique asymptote at y equals x. So the line y equals x has a y-intercept of 0, so it's going to go through the origin, and its slope is 1. So we're going to rise 1, run 1, rise 1, run 1, rise negative 1, run negative 1. So if we just dash this now, there's our oblique asymptote. So now, roughly, our graph is going to fit in this grid. Now if you look, our grid is now tilted because of that oblique asymptote. So we're going to have a piece of our graph, a branch, either here or here, and then a branch either here or here. And we can see on the calculator which ones it's going to be, but we can also use our intercepts to see that. So we have our x-intercepts of negative 3, and 2, and then we have our y-intercept of negative 6. So just from those intercepts, that confirms that we will have a branch in this part of the grid, not down here. Remember, we can't have a piece of the graph, a branch here and here, because that would fail the vertical line test and it wouldn't be a function. So you can just sketch the shape. That graph is approaching that line, getting closer and closer to it, and we saw when we zoomed out, on the ends, it essentially looks like a line. It looks like that line. And then we've got our other branch. If we connect our intercepts here we're approaching, and here we're approaching that vertical asymptote. And then we'll talk about our behavior of the function around the vertical asymptote. So here's our vertical asymptote, the split. So we've got a branch on the left and the right. So as we approach from the left, our y values get infinitely larger. So we can say as x approaches negative 1 from the left, q of x approaches infinity. And then as we approach from the left branch, as we trace along here, our y value is getting smaller and smaller as it approaches that vertical asymptote. So we can say as x approaches negative 1 from the positive side, from the right side, q of x approaches negative infinity.